All right, let's get right into it. You could argue that the entire universe, all of physics, really just boils down to two of the simplest questions imaginable. And we're going to explore them through the lens of one of the absolute masters of explaining things, the one and only Richard Feynman.
And here they are. That's it. Where and when. Where is something? And when is it there? Seems simple, right? But for most of human history, answering these wasn't about science at all. It was all about debate, about argument. It was philosophy.
Yeah, you had thinkers like Aristotle, who would basically deduce how things ought to move, just by using pure logic. But then, a few centuries back, this guy Galileo comes along and basically says, you know what, that's a nice thought, but what if we actually measure it? And that one simple shift in thinking, it completely changed everything. It's pretty much the birth of modern physics as we know it.
So this brings us to our first section, the physicist's first question. And it's a good one. How did he actually do it? How do you measure something moving if you don't have a stopwatch? They didn't exist. This is where Galileo's practical, hands-on genius just really shines.
Okay, get this. It was so simple, it was brilliant. He just let a ball roll down a gentle slope. Now for the when part, the timing, he used the only consistent clock he had on him, his own pulse. Seriously. So thump, make a mark where the ball is. Thump, thump, make another mark. Thump, 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 a third mark. The genius here is in the simplicity. He wasn't just casually watching, he was systematically logging where the ball was at specific whens.
And what he found? Well, this is the payoff, right? He discovered a pattern. The distance the ball traveled wasn't just random. It was directly proportional to the square of the time. This wasn't some philosophical opinion anymore. This was a physical law, a hard and fast rule of the universe, born from one simple act, deciding to measure.
Next up, clocking the universe. So that whole experiment hinged on measuring time. But what even is time? It's a question that could really bake your noodle. So let's dig into that, and we'll start with a definition that is just pure classic Feynman.
I love this. Time is what we already know it to be. It is how long we wait. He just cuts right through all the philosophical fluff. For a physicist, the important thing isn't some deep, abstract definition of time. It's about how you measure it. And to do that, you need a clock. You need something that repeats over and over again, something periodic.
So for ages, our standard clock was, well, the Earth itself. One full spin is 1 day, right? But the thing is, as our instruments got ridiculously precise, we figured out that the Earth, it's a little wobbly. It speeds up and slows down by tiny, tiny fractions. So we needed a better clock, and we found one in the vibration of atoms. These atomic clocks are just unbelievably accurate. We're talking so precise they might lose 1 second over hundreds of millions of years. And with that kind of precision, we can start to measure time on some truly insane scales.
And when I say insane, I mean it. Check this out. Physicists have measured the lifespan of certain subatomic particles, these little resonances, that exist for only about 10 to the minus 24 seconds. That number is so small it's basically meaningless to us. Think of it this way. That's about how long it takes light to travel across a single proton. It's just an impossibly brief moment of existence, the shortest slice of waiting we've ever clocked.
Okay, so we've got the super, super short times covered, but what about the other end of the spectrum? What about the ridiculously long times? Like, the age of the entire planet. We obviously can't just count the years backwards. We need a totally different kind of clock for that. And luckily, nature has one built in for us.
And that clock is radioactivity. It turns out the decay of certain elements is incredibly predictable, like a perfect cosmic metronome. You take something like carbon-14. We know that every 5,700 years or so, half of it will decay into something else. That's its half-life. And that's fantastic for measuring things on human timescales, thousands of years. But for the really, really deep past, we need a slower clock. That's where something like uranium-238 comes in. Its half-life is about 4.5 billion years. So by looking at the ratio of uranium to what it's decayed into inside a rock, we can literally read how old that rock is. And when we use that uranium clock on the oldest rocks we can find, and on meteorites left over from the formation of the solar system, we get this number, 4.5 billion years. Just think about that. That isn't a guess. It's not a belief. It's a measurement. So from the flicker of a particle to the birth of our entire world, we've actually managed to put a number on when.
All right, section 4, mapping the cosmos. We've tackled when, now for the other side of the coin. Where?
We're going to take that same journey, starting from something we can almost wrap our heads around, and then just zooming out to the truly mind-bending.
So, let's start nearby, with the moon. How do we know how far away it is? Well, we can bounce radar signals, or even lasers, which is super cool, off its surface and time how long it takes for the reflection to get back. Simple, right? Using that, we've pinned it down with incredible accuracy. It's about 400 million meters away. We're basically just taking our ruler and extending it out into space using the speed of light.
But what about going even further? For that, we need to get a lot more clever. Astronomers found this amazing clue. They looked at these big, ancient balls of stars called globular clusters. And they noticed they weren't just scattered randomly across the sky. No, they seemed to be swarming around one particular patch of sky. By mapping them out, they realized these clusters were all orbiting a single, invisible point, the center of our own galaxy, the Milky Way. And the distance to that center? A jaw-dropping 10 to the 20 meters.
And it just keeps going, using even more ingenious tricks, like using exploding stars and distant galaxies as standard measuring sticks. We can map the universe all the way out to the farthest light that has ever had time to reach us. And that gives us this number. This is pretty much it. This is the edge of where, the boundary of our entire observable universe.
Okay, let's take a breath. We've gone out to the biggest scale there is. Now for our next section, beyond the ruler. We're going to do a complete 180. We're going to slam the spaceship into reverse and dive down, way, way down into the world of the impossibly small.
So, an atom. You obviously can't just look at one with a microscope, not even a really good one. So how in the world do you measure it? Well, one of the clever ways is to shoot X-rays at a crystal. The X-rays bounce off the neatly arranged atoms and create a specific pattern. And from that pattern, we can figure out the exact spacing between the atoms, which tells us their size. It's about 1/10 billionth of a meter. It's like we had to invent a whole new kind of ruler for this tiny world.
But wait, there's more. Deep inside that already tiny atom is the nucleus, which is about 100,000 times smaller again. It's just staggering. So how do we measure that? Well, Feynman explains it as a kind of cosmic dart game. You take a really thin piece of foil and you just fire a stream of particles at it. By counting how many particles actually hit a nucleus and scatter, you can calculate how big of a target that nucleus must be. We call it its cross-section.
And this is where things get really weird. This is where Feynman pushes us right to the very edge of physics. We've gone on this incredible journey from Galileo counting his pulse to measuring the size of a nucleus. But what happens if we try to go even smaller? Do our fundamental ideas of where something is and when something happens, do they even make sense anymore?
Well, it turns out the answer is maybe not. Nature itself seems to draw a line in the sand. It's called the uncertainty principle. And what it says is that you fundamentally cannot know the exact position and the exact momentum of a particle at the same instant. And the same rule applies to energy and time. It's not that our tools aren't good enough, it's that reality itself has a built-in fuzziness. The universe literally forbids perfect, absolute precision.
And that's where we have to leave it. We started this whole journey with Galileo measuring a rolling ball with his own heartbeat, and now we've gone so deep that we've reached a place where our very concepts of a specific where and a specific when start to get blurry and break down. It leaves us with this incredible, fascinating question for the future of physics. If we want to understand the very fabric of reality, do we need to invent a completely new way to ask our two most fundamental questions?